so what we have here is the heating curve graph for a substance. This is not water. I know it's not water because you're looking at the melting point. The melting point is not 0 degrees Celsius. So, Coach Campus, how did you get the melting point there? Well, first of all, we got to know that in this region right here, we are heating this substance as a what? Solid. So from this point to this point, we're heating this substance as a, we'll put a line down here, solid. You can write solid in here on your papers if you like a diagonal solid. Mine would be messy, so I'm not going to do that. All right? So from this point to this point, we're heating this substance as a solid. Okay? What do the molecules look like? Tight. Tight. Good. Well, don't you move on me. Okay? All right? So then, what process is represented here? We just talked about that. What process is represented there? That is the process of going from a solid to something. Liquid. To a liquid. So you're, oh good, you're already making the conjecture that this is a liquid, and you're right. That is the liquid state. Liquid. So then the red line represents what process? Melting. Good. So the red line represents melting. Now, you probably would do better by writing that in up here, like this. I didn't want to because I knew it would be just what happened. Very messy. All right, melting. Okay? So we've got from this point to this point, it's a solid. From this point to this point, we're melting. This point to this point, it is a liquid. Okay? So who can help me finish now? What would this point to this point be? Vaporization. And then here the substance would be we'd be heating that as a gas. And so the molecules would be totally spread out like this. Here the molecules would be just a little bit more spread out, right? But not too much where they're able to slide by and flow. Okay? Now, anytime you have a graph and numbers, the numbers mean something. So now I want to see if you've been paying attention. So if I take this line right here and draw it straight over, that is the what? Temperature at which melting occurs. What would that be called? What would we call that? Melting point. Yeah, melting point. Okay? And so if we do a line here over, that would be the temperature at which, what is this process? Vaporization. The temperature at which vaporization occurs, which we call the boiling point. Now, one more thing I want to remind you of. This is very important. As the temperature increases, what can you say about the kinetic energy?
It increases.
So in what regions do we find the kinetic energy increasing as temperature increases? Here, this point to this point. Kinetic energy is increasing from here to here. Kinetic energy is increasing from here to here. The molecule is moving faster as temperature increases. Now here's the situation we have. There's two places on this graph where in fact the temperature does not rise. If we did this in Chem 2 and we got close to the melting point, all of a sudden it would go 2 or 3 minutes and you'd be like, Coach Camus, the temperature's not rising any. Something's wrong with our thermometer. You always say that in Chem 2. All right, and I said, no, just let it go for a while. For some reason, we have the temperature at a constant here. So what would you say about the kinetic energy here and here?
It stays the same.
It's constant. What do you know what exists as the opposite to kinetic energy? Not the opposite, but they work in verse. Potential energy. Okay, ions coming in here in just a minute. And so if kinetic energy is at a constant here, then potential energy is at a rise. It's increasing. So our statement is potential energy is increasing here. Potential energy is increasing here. Now let me say that another way. Potential energy is increasing during the process of melting. Potential energy is increasing during the process of vaporization. Why? Why would the molecules need potential store up energy? Why would they need to store up energy in the process of melting or in the process of vaporization? Why do they need to store up and gain all the energy from the surroundings at those points?
To be able to change states.
Okay, that's right. To change states. What is required for them to be able to change states by using that energy? Break away from intermolecular forces. So the answer to this, and most students miss on the test, I say explain why the temperature remains constant in those two regions on this graph. The answer is the molecules must absorb and store up all the energy possible in the surroundings as potential energy in order to break away from their intermolecular forces.